Alright, so now we'll quickly talk about multimodal alignment, how now text only models can move further up to other modalities like audio, like video, images, all those, right? Including more recently into newer domains like finance, like biomedical, like health data and whatnot. So this is again that fundamental big picture that if the subsequent, let us say, stages are you know of your focus, this is the one key picture that I want you to take home. Most of the models, I'm not saying everything has it, most of the models, at least till say last year, at least till let us say major publications happen around those models, reports happens around those models, they take a view of alignment. They take a view of that the core structure of what we discussed remains the same. All I need to do is convert other modalities into sequence of, let us say, units, for lack of other words, or tokens, the way we discussed, and now take the sequence of tokens along with text, align all of them, so that the core, let us say, ask from the model is that the reasoning, the knowledge is built largely from a text world, and now you are accessing those knowledge with other senses, other modalities. So if I want to basically ask a question about Bangalore weather, the knowledge may be derived from a weather website in the textual form, but my question in an audio form needs to access that information. And the output also, if you want it in an audio, then it has to be converted, realigned to an audio output that conveys the same information that was derived in text. There are both plus and minus to this view of multimodal alignment. The plus is the resource in the text setting is significantly higher, right? The ability to mine, the ability to generate new text, right? Once these models came up, the internet and everything started further getting flooded with more and more, let us say, data points from the text world. So now what has happened is the textual presence is significantly high. So potentially knowledge resources are richer in a text world. You could argue that for some cases that is not the case, but largely this is the view. And the negative or the con to this therefore is, you ask the same question as we said, what is the weather in Bangalore? In text, while you ask the same question in audio form, you might get a different response because the alignment is an requirement. How do I say that this is the same data point when expressed in a different modality? This becomes a difficult issue. This is why you say there is a modality gap. This is why people have put out papers, benchmarks on the same thing replicated in different phases, different languages if you want to ask, different modalities if you want to ask the same thing, and then said that there is a modality gap. The core reason for it, even if you say all of them are multimodally trained, fundamentally the model's capability is higher in predicting a temporal sequence of tokens, and no matter, let us say, how you reconfigure an image as a sequence of tokens, it is a spatial input, right? While you have converted it to a temporal sequencing, it is a spatial input that still requires some other massaging to become this temporal form, and therefore there is some alignment loss. Okay? So keeping that perspective in, what we do, say an audio, say an image and all that, you pass it through some level of encoding models. Again, some of them could be pre-trained using encoder only transformer architecture that we discussed in the last session. Once you get some representations, then you start doing some sort of an alignment. An alignment typically means that you have some response of input in one space, and then the model has to respond in some other modality, say text, right? So think of it like a graphical input, but a textual description of the graphical input could be your text. So you want to align what an image says in terms of text to what you see as a pictorial representation of it. And this alignment is crucial because that is what drives it to map all of them to the same access points within the model's core knowledge resource. Right? And then when you pre-train also, you want the model to be fundamentally multimodal. The first generation of models, the GPTs and other models, they were inherently text only, and you only trained in peripheral encoder, peripheral alignment adapter models. Subsequent generations of these did not follow that. They started pre-training also with multimodal data. Let me just talk a little bit more deeper than this. So, for example, the common ones, people use vision transformer based image encoders, people use beats or spectrogram based audio encoders. Again, I am not going into domain specifics of any of this. There are space-time VIT models which try to encode video data into a sequence of vectors. And if you take other data like 3D data, like speech, which is more like a semantic understanding of speech, you can do whisper-like models, tables can have table embedding models. There is a plethora of encoder models for different domains, types of data, types of information that you want to derive from the data, etc. You can line a subset of them based on your applications and now take those outputs. Either you can adapt them jointly with the large language model or keep them as frozen encoders and just align the representations that come out of it through some lightweight adapters. So let's see an example maybe that makes it extremely reasonable. Right. So let's say this is a visual captioning task, right, an image captioning task. Maybe there are some images that you can see. I hope some of you in the back can also see the images, but somebody playing tennis is one of the images, an animal eating grass, an antelope eating grass is the other image. So what you will do is, while pre-training, you can also interleave the modalities so that the alignment is fundamentally inbuilt. Right? You can basically take image tokens. Right? As you can see, image tokens are colored in pink, purple pink, and the text tokens are colored in green. So the image tokens, which are these, can be interleaved with the text tokens before you pass the next image. You can also do it in between. You don't have to align all the tokens of an image and then pass the text. Right? You can also further split it further apart so that the models further learn to align it. Right? So in an audio world, the equivalent of this would be, let us say, if you say the antelopes are eating grass, maybe the eating grass, I want to make it speech. So then you will say the text tokens up to antelopes are preserved, and now eating grass becomes a speech tokens, and those speech tokens get appended to the end of the text sentence or to the partial end of the text sentence, and then you also indicate to the model that which subset of the tokens are speech, image, text, etc., and therefore the model also understands that a token or a modality conversion has happened. Now by doing this, right, similarly for the second one, now what happens is particularly multimodal tasks become very easy. Now you can ask the question, for example, the image plus what is the boy doing, then the response is something like flipping his skateboard. You can also generate, right? So essentially give an image and generate a free flowing text of it, right? You can also generate multimodally, right? Now take an image, make it swim in the water, right? Now your cat has to swim in the water, so now it's an image generation output, which actually means you essentially have a multimodal output option too, where the image tokens are the ones that the model is outputting based on the original image tokens plus the text. Right? By feeding in during the pre-training itself that both input side and the output side have next token prediction tasks that are both multimodal, you enhance the inherent multimodal capabilities of this. But this all comes with a cost, right? So now we talked about text and text tokenizer. You have to compress and tokenize images, audio. Your token space at the output becomes significantly large, right? Which is why you have more hallucinations, more issues. Secondly, when your token space is so large, it has to see that much more data to essentially have representations that make meaning, right? An image is a very structured set of tokens. Not every sequence of tokens, even in the image setting, comes out with a meaningful natural image. So, to make sense of the semantics of those tokens, the language modeling of those tokens significantly is data intensive. So, that is why only the big models, only the large size models with heavy training, with heavy intense compute that has gone in, can handle these in diverse multimodal data. Right? Otherwise, you are going to be restrictive, be it languages, be it modalities, be it tasks that you want to consider, because all of them require alignment. Right. So, then the last hour or so, what we will spend on is on the pre-training and the post-training of models. So, let us talk a little bit about the pre-training part, and then we will take a break and the post-training will be after that. So, we started talking about the objective, and most of the models, there are some flavors and variants around this, but you can assume that most of them fall into this line of predicting the next token, right? A loss that is listed, even we talked about this loss in the last section, last session. All the objective tasks like a question answering, like a summarization, like an image description, like an audio captioning, like generation of anything new can be represented in the task world as a completion. You are giving a partial input, be it an instruction based, be it a non-instruction based, the model has to follow that prompt, right? So what I am going to do for the post-training side, I am going to take a bunch of core views from this a review paper that came in. This is talking about LLM post-training, right? So the pre-training provides a broad foundation, right? But most of the model developers don't give you the pre-trained model output, right? Because it is not very specific to any task. It is very raw. It is very wild. It has just broadly understood modalities of text or audio or images, but you need post-training. Once the pre-training on auto-completion or next token generation is over, you need to structure the model weights to be good at some subset of tasks, right, on which you are going to play with them. So, the three sub-aspects, right, to improve their reasoning, to improve their factual understanding or an accuracy, to align them with user intents, etc. The three sub-directions that we will talk about, in fact, two of them is only what I have prepared for this session, on fine-tuning and on reinforcement learning. The test time scaling, hopefully we can talk about it in the next class. But where do we place this, right? We always want to see the big picture first. Where are all these going, right? Where is it? Why should I even care about post-training? Because as you see here, the core nucleus is the pre-trained models, right? Now you have to do post-training, and all the models you see at the periphery is the set of models or subset of models that you and me are using on a day-to-day basis in the LLM era, be it the GPT series, be it the Gemini series, the Llama series, the Quen series, the DeepSeek series. So all of them lie in the periphery, and between the two core nucleus being the pre-training and then the delivered products being the model outputs that you see, these are passing through different sets of fine-tuning or post-training. And if you see that, fundamentally the next layer is a broad classification around fine-tuning, around reinforcement learning, and around scaling, right? And you can always use a subset of combination of this. I can do a fine tuning plus a reinforcement learning, I can do a fine tuning plus a reinforcement learning plus a scaling. I have not defined all this, but I am just giving the broad picture that takes a pre-trained model, the journey that a pre-trained model takes to become your inference model that is served in the public space. Right? So, plethora of publicly released models fall under one of these buckets. They are broadly categorized based on this reinforcement learning, scaling and tuning. And the whole post-training is a big process. Right? As you see, pre-training is a big compute, big data intensive modeling step. The post-training has a lot of engineering, lot of machine learning prospects that make the models rich into some subset of tasks, and that is what basically sells these models. So let's quickly walk through that set of things. So let's start with the first one, which is on fine tuning. It's very simple again. Again, you can think of the fine tuning as an extension of the pre-training, except that the data is structured. You are not going to say any part of the sentence and ask it to fill rest of the sentence. You are going to start and stop these inputs and prompts in a structured way. It has to be like, what is the weather in Bangalore? I can't just say what is and ask the model to predict weather as the next one. I have to give a full structured input as what is the weather in Bangalore, and then the answer is the full slot it has to predict. So you create a structure on the data that was absent when you did pre-training. During pre-training, you can't go and, let us say, curate a weather data output into questions and answers. You just leave the raw data of a weather website as is and learn the next token prediction in a random fashion. But in you fine tune, you force a slot filling structure. Domain specific applications, like, for example, if I want to do medical diagnosis, I want to have question answering in a medical space, right? So you might have seen some of these reports that come out increasingly. What are these models used for, right? A subset of them particularly get used for medical advices, although never really, they have not been trained for this. So now as a model developer, you want to start seeing, okay, this is the set of queries that are coming. Maybe I have to curate it so that I don't have a wild response. I have a curated FAQ, right? Frequently asked question data set. I want to give those questions and force the models to respond to the FAQ answers that I have in my repository. Now the model becomes a very good medical advice chatbot, right? So, but what are the key issues, right? As we said, fine tuning is very simple, but it has issues. Typically, when you fine tune it, it becomes very special. It becomes very good at that task you want, but it loses its general capabilities. We can do like, medical advice, right? Right, and then, if you ask, let's say the question, right, what is the weather? It might say, it's time to eat rice, right? So these kind of responses that align with what the model was trained on will come out. So now is generalization to new tasks. So then people started worrying about this. How can I keep the specificity that I want, but not compromise on the generalization skills? Then the obvious next aspect was something called instruction tuning, right? So most of the models that you see, even as SFT or supervised fine tuning, they are actually instruction tuned. So what is an instruction tuning? You provide detailed instructions, right? You basically say, okay, summarize this piece of text, and this is what the summary is. You say that, okay, now I want to answer questions. So you provide that your job now is to answer questions that are given in the question form. So you define an instruction for each task and you give the prompt. So the model now has to not just fine tune on one type of a question answering chatbot, but it also has to have the capability for summarization. It also has the capability for creative generation and whatever task that you want to have that specialized on. And now you can start seeing whether they actually do even something that is new. If I do multiple tasks and I force the model to listen to my instructions, is it going to have this instruction following behavior even beyond these tasks? Turns out that one of the most popular papers in this is called the FLAN, right? This is fine-tuned language models as networks. So FLAN essentially means that you fine-tune on a set of tasks and the model becomes even more generic. So let us take a model and then we take a set of tasks on which you fine-tune with instructions specifically for each task. Now the model also can become a zero-shot learner. A zero-shot, as we discussed in the last lecture, is when you have not introduced that task. You are asking a totally new task, but since you have made the model follow instructions very specifically and there were varied tasks in your fine-tuning, it suddenly becomes more generalizable. So what is it, right? So let me just kick a quick deep dive into this paper itself. Okay, so one of the tasks is, say, common sense reasoning, right? So basically, how do I, here is a goal, how do I get a cool sleep on a summer day, right? So then you basically give options like, keep your pillow in a fridge and whatnot, and basically have this as a target for the model to train. Now say another task is to translate, say you want to translate to Spanish. Now there could be several other tasks like sentiment analysis, like co-reference resolution. All these are language modeling tasks. These are essentially tasks that the paper used for showing this. Now what you do on a completely new inference task, right? So what do I do basically to respond to a completely new inference task? Maybe the question is, two pieces of text, do they entail? Meaning, do they follow each other? If the two pieces of text agree or follow each other, you want to get a yes or no answer, and the FLAN now says correctly that it is not possible to conclude this. Right? So as no, it is not possible to conclude. Now the model responds with, it's not possible to tell. Although this whole kind of entailment task was never part of the fine tuning or the instruction tuning subset. Right? So you have now essentially made a model that basically they say with GPT-3 zero shot, GPT-3 with a few shot, and then you have the FLAN with zero shot for a set of unseen tasks, and the FLAN even with a lesser size performs better on language inference, on reading comprehension, on closed book question answering, all those kind of tasks that the paper listed, and it has become, right, the leading point for several others. So many of the models you will see, the variants you will see in Hugging Face, they would write instruction tuned certain size, right? This actually means they have instruction tuned on a set of tasks that they thought are very common and useful, but also has the capability to generalize beyond the task that they could consider. So to summarize, or basically to say what is the difference again, what are the pros and cons, or maybe a graphical illustration. So if I basically want to do fine tuning, I would take a task A, right, and then I would just take that model and then create a copy of the model that is very specific to that task A. But I can do with a single model and instruction tuning for multiple tasks and still do the task A which was unseen, and now you start seeing that the instruction tuned is way better than a zero shot or a few shot, but maybe not as good as the fine tuned one. But now it also has other capabilities. It is not as specific as the fine tuned one, right? To just summarize fine tuning versus so-called instruction tuning, you are essentially enabling the model to follow instructions. You have forced it, right? For the same piece of text, you could ask a question at the end of it, and now it has to understand that it's a question answering task and respond, as well as you can have a summarization for the same piece of text and then it has to respond differently. So if you say the large chunk of it, say, could be this slide, right? The large chunk of it could be this slide. Maybe I want to ask the question whether, let us say, the computational complexity, is it listed in this table? Right? That's a question answering task looking at this table, and the answer is no. But you could also say, now given this table, summarize it. Right? So the table remains the same, means that the graphic, the image that you see on the screen remains the same. The tokens which are largely part of that input remain the same, only the instruction has changed. And you have forced the model to say that, follow the instruction carefully, so that you can't respond in the same way. Even though the large part of the input sequence is identical, you still have to respect the instruction. So that is pretty much basically a summary of being a general assistant, very conversational. Because it follows instructions, you can keep repeating or revising your instruction, then it starts generating different responses, so that now you know which is the right instruction to do. Right? The whole set of prompt engineering, if you ask me, a lot of it comes from this FLAN. Now that you know that what is the right instruction to do, because the model knows to follow when you give the right instruction. So then the question was back to us to form that right instruction, and therefore this all is due to the FLAN setting. So we'll take a short break. Thank you.